Hello, good morning everyone. Dr. Bennett here, and welcome to a little mini series regarding aircraft takeoff and landing modeling. So let's start in this first video with the takeoff. So here's our airplane sitting initially stationary at one end of the runway, and essentially what we're going to look at is trying to figure out how much distance we require to take off given the airplane's characteristics. So here's just a little diagram of the forces acting on the airplane during the takeoff roll. So I've color coded the force vectors, blue being in the perpendicular direction and red being in the parallel direction. So in the perpendicular direction we've got the lift force acting upwards, and then also the normal force acting from the runway on the airplane acting upwards, also supporting it as it sits there on the runway. And then we've got the weight of the airplane acting down from the CG location. And then in the parallel direction we've got the thrust vector positive, and then we've got the drag vector negative in this direction, and this is the rolling resistance coefficient mu. So I guess between the airplane tires and the runway, right? That's acting to slow us down also, right? So this rolling coefficient of friction mu is assumed to be somewhere between about 0.02 and 0.04 for a paved runway. So if we want to put some values into that, we can use a generic value for that. So over here I've just used Newton's second law, F equals ma, to sum the forces in both directions. So in the parallel direction, F equals ma, I've got positive T and then negative D and negative mu n. Then in the perpendicular direction, I've summed the forces ma, so A here is our centripetal acceleration, right? Where R is the radius of like an arc if the airplane was pitching. So I guess if the airplane is traveling horizontally along our runway, then the radius of this arc tends towards infinity, so we can assume that this side here is 0. So let's just go ahead and label that. And so we have positive N, normal force, positive L, lift force, negative W equals 0, and so therefore we can rearrange this equation to just give us the normal force, which is just the difference between the weight and the lift. So from there we can model the takeoff acceleration just using the first equation up here. Ma, so mass is just weight over g, and I've been specific to label the takeoff weight as W sub TO for takeoff, and then that's multiplied by A. And again, I've given it the designation TO for takeoff acceleration, just to distinguish it from the landing modeling that we're going to do in a minute. So T minus D minus mu n, and we just said up here that n from the perpendicular summation is just the difference between W and L. So I've just replaced n with WTO minus L from here. So that gives us our takeoff acceleration if we just take this piece here, which is equal to that, and just multiply both sides by g, divide both sides by WTO. So next, we have to do a little bit of an intermediate step before we get to the takeoff distance required by calculating the takeoff time. The reason for that will be obvious in a minute. But in order to do this, we need to make an assumption about our takeoff speed. So the convention here is to assume that our takeoff speed is 20% higher than the stall speed of the airplane, so that it gives us a little bit of margin over the stall for safety reasons, right? And we know that the stall speed corresponds to where the maximum lift coefficient occurs. So using our lift equation, L, magnitude of lift, is equal to CLQ, which is dynamic pressure multiplied by the wing reference area. So the equation for the dynamic pressure is 1/2 rho v squared. So if we know that these two things correspond, then this equation, if we assume that where we first become airborne on our takeoff is where the lift is equal to the weight, so that's just before, at the split second when we first become airborne, WTO, which is equal to L, is equal to the right hand side of this where we have CL max and V stall. So we can just rearrange this equation for V stall. So that comes from here, just rearrange the rest. We'll end up with this square root when we take the square root of V stall squared. So then once we have that, we can obviously just plug that expression into this assumption over here. So 1.2 multiplied by all of this. So then if we note that our takeoff acceleration that we just calculated the expression for up here is just the change in speed over the change in time, delta V over delta T, and we're assuming that we start off stationary, so with 0 velocity at time t equals 0, then rearranging this, we just get the time required to take off is just V over A takeoff. So now that we have this, we can calculate the time required to take off just by plugging in our expressions for VTO from here and ATO from here, which is what I've done there, and rearranged it to get this. Now, as I say, that's just a kind of stepping stone to get us to something a little bit more useful, which is the takeoff distance required, which I started to do over here. So takeoff distance, the nomenclature for that is S sub TO. And if we realize that the distance is just the integral of the speed with respect to time, why? Well, because the derivative of the distance with respect to time is the speed. So therefore, the integral of time, the integral of v with respect to t gives us distance. And also, the speed we know is just dv by dt, which we did right over here, look. Then, if that's true, then just again rearranging this for v gives us AT equals v. So from here I can just go ahead and differentiate it, integrate it with respect to t. So A in this case is just a constant, so the integral of t with respect to t is just t squared over 2 to get this. And so from here, we now have all of the pieces to plug into this expression. We've got the acceleration, the takeoff acceleration, which we did back over here, and we've got the time required to take off, which we did down here. So this is going to become a bit of a mess because we're going to have to plug in those long expressions for ATO, which is this one. Here's our factor of a half from here, and then this is the time required, which we derived down here, all squared. But it actually tidies up not too bad to get this. So in particular, take note of this factor of 1.44 in the numerator, which comes from 1.22 squared from this part of this expression up here. So this is our takeoff distance required, given all of these characteristics associated with our airplane. So let's just have a look quickly at the individual terms, because generally the goal is to minimize our takeoff distance, right? Because that's going to mean that we can get in and out of more airfields and airports, right? If we're limited on runway distance, for example. So this expression is minimized, obviously, by minimizing the terms in the numerator and maximizing the terms in the denominator. So takeoff distance is minimized for lower takeoff weights, obviously. Then maximizing air density, so that will occur at low altitude, and lower temperatures will also yield a higher air density as well. And this is why you sometimes see airplanes get grounded and prevented from taking off on extreme high temperature days. Think about places like Las Vegas or like Phoenix, Arizona, for example, where the temperatures can exceed well over 100 degrees F, right? If the temperature gets so high that the air density reduces significantly, that's going to extend our takeoff distance, isn't it? So that's why certain airplanes, think about big commercial airliners, for example, like 777s, A380s, big heavy airplanes. If the temperature gets too hot, then the takeoff distance actually can get too long for the runway in question. So that's how that all kind of lines up. Takeoff distance is minimized for higher wing reference areas. So this is why certain airplanes have Fowler flaps. If you don't know what those are, check those out. They are flaps which are designed to not only adjust the camber of the wing, but also to extend the trailing edge so that you get a higher wing reference area, which will then minimize your takeoff distance and also landing distance, as you'll see in the next video. CL max, well, that's determined by the airfoil itself, and as I said, the flaps to adjust the camber. So that's kind of an aerodynamic consideration. The acceleration due to gravity, which occurs down here, is lower at lower altitudes. The difference is fairly small, but I mean, it makes a difference. And then we're into this kind of bracketed term here. Higher thrust, obviously, that will shorten our takeoff distance. So considerations there about the power plant or the propulsion system of our airplane. If we have the ability, we might want to employ afterburners, right, to shorten our takeoff distance. Like, think about like fighter jets taking off from an aircraft carrier, for example, where the distance is severely limited. Lower drag down in here, and then we've got the rolling resistance term. So obviously if we have a lower rolling resistance, then we can get airborne quicker and in a shorter distance. And then finally a higher lift value in there, which again is tied to this aerodynamic consideration right here and our wing reference area as well. So that's aircraft takeoff modeling. So join me in the next one for aircraft landing modeling. Thank you guys.